tree. So a tree or a graph that is connected and has no circuit. So I just put down this image. I just Google it and copy paste here. I want to show you that what is tree. You know, if you walk away from your house, step outside, you see a bunch of trees out there. All trees are basically open, but it's connected to the root. It's very rare you see a box or connected unless otherwise genetically modified. Okay, so again, it's just a traditional tree and their leaves are connected with the roots. So I can create one to the right side actually. So I want to create, so this is the tree coming down, and of course one down there. It's like that, you know, I mean, you can have leaves. Those are leaves basically you can have. Okay, so these are basically trees disconnected. As you see, there is at least one path. At least you can go through here, you can go through here, go through here, go through here, go through here. It's often as you see. That is my point here, okay? It's not a circuit. It doesn't form any circuit. It's often. So therefore it is called a tree. Now I can actually create a couple of more here actually. So if I have this one here, very simple one, I want to make up here. Obviously, this is a tree. Why? Because everything is connected and it's often. You can go through everywhere. So this is a tree. Okay? I can even make it more complicated. This is also tree. As you see, it's often, it's connected. Okay? Now I can make things more complicated also. This is also tree, yeah. Yes, yes. But if I look into this one here, if I look into this one, this is not a tree. This is not a tree. Not a tree. Okay. Why? Because this is open, but it's not connected. Okay. This is two tree, you want to say. Two of them individual. This is not a one. Okay. So this is not a tree. We can have a little more actually. Here you go. Let's take a look. Can we have more? Yeah. So I can create one here, right? Is this a tree? Not a tree. Why is not a tree? Because this is forming a box or circuit. This is like a network. As you clearly see, each vertex are connected. So, well, this is not a network. This is a graph, but this is not a network. Okay, in order to be network, this has to be connected too. So this is not a tree either. Okay, so clearly as you see. Now, is there more? Yes, absolutely. So let's take a look here. I can make up another one here. Is this a tree? No, it is not a tree. Why? Because of this one. In order to be tree, you have to open up one of those in order to be tree. Okay, so that is called the tree. Well, and of course, which is spanning tree. So we're gonna learn what is spanning tree now. A spanning tree that is created from another graph by removing edges but keeping a path to each vertex. Okay, let's talk about a spanning tree. How do you do that? Let's take a look here. I'm going to have this one here. This is a graph. By the way, this is not a spanning tree. In order to find a spanning tree, we can actually just remove one edge. Well, just remove one edge, then it's going to be spanning tree. Let's do more. So this one is a little bit complicated, more complicated as you see. But can we make a spanning tree here? So we have to remove the edges. We have to remove the edges. So what I'm going to do here is basically I'm going to remove the edges. I need some kind of ink here. Okay, let's take a look. So I can remove these edges. It's connected each vertex, so I'm going to remove these edges. It's connected. Okay, so I'm going to remove these edges also. I need to open up, but the vertex must be connected, and I'm going to open this one up, and I'm going to open this one up, and obviously I have to open this one up. I need to open maybe any one of them. Still, this is not a tree. It's not a tree or even a spanning tree, so we have to remove it, this edge too. So I can remove this one, this one, this one, or that one. So it's up to you actually. So I'm going to remove this one. Look at this. This is now on a spanning tree. Okay. So yes, this time is, yes, it is a tree now. It is a tree now. Okay. Let's talk about minimum spanning tree. So minimum spanning tree is a tree for which the sum of the numbers associated with the edge is a minimum. Edge is a minimum. So how can we actually find out minimum spanning tree? So minimum spanning tree, let's actually have this one here. This one. So this is a graph A, B, C, D. And this has a value 4, 3, oh, so let's make it 4, 2. And let's make it 3, 3. Remember, the easy and short way to find the minimum spanning tree is just look into each box. Look into each box carefully, each figure carefully, and remove the highest edge. Remove the biggest edge. Once you can remove the biggest edge, I'm going to remove this one. Look, as often as you clearly see, we have all the vertices connected. So our minimum is going to be the sum. Look at that here. What is sum? Sum means 3 plus 4 plus 3. So that is going to be 10 is the minimum spanning tree. So we do this to go point 1 to point B with the shortest distance possible. Nowadays, when you drive, you use OS, Google, and all those. Basically, used to be Yahoo, Yahoo Mail, Map, and so on. Now, you most probably ending up with Google Map or OS. So if you do so, you clearly are using the same technique. You're going with the minimum route, minimum possible route. So this is how actually it works out in the software. They code it and they just come up with that quickly. Okay, so I'm going to actually have another example. Doesn't matter how it looks like. Okay, not all the neighborhood has a straight line. Okay, so you can think of that. Okay, now I'm going to actually label them. So 2, 1, 2, 2, 2, 4, 3, 5, 4, 3. Okay, so what is the minimum spanning tree? So guys, easy and simple, easy and simple. You just remove one of the edge, which is the highest in each figure. So if I go with this figure here, right? If I go with this figure here, this figure is basically 4 is bigger than 2, 3. So I can erase 4. If I look into this figure, 5 is bigger. I can erase this 5. If I look into this figure, 4 is bigger. I'm going to erase this 4. If I look into this figure, well, any one you can erase because all of them is 2 is going to be part of your answer. So let's take a look here. Let's erase it. So I'm going to erase this one here. As you clearly see, I'm erasing that, the biggest edge. I'm erasing this biggest edge too. That will give us a minimum spanning tree. Minimum means the sum of the edge, which is minimum. So clearly, as you see, I erased that, right? Oh, sorry, there is a little bit mistake I think I did. Yeah, that figure doesn't have, 3 is not the biggest, so 4 is biggest, so I'll have to actually erase 4. Sorry about that. And finally, I can actually erase one of those, and everything is open. All the products are connected. So in this case, my minimum spanning tree is going to be 2 plus 2 plus 2 plus 3 plus 1 plus 3. That is going to be 4, 7, 9, 10, 11, 12, 13. So that's 13 is the minimum spanning tree, clearly as you see. So I'm going to make up one actually. Again, I'm going to erase it. I need another one here. Okay, so I have this one here. That would be nice enough down here. I can label it now. 4, 4, 6, 6, 9, 5, 2, 5, 4. And the question here is asking if each edge represents feet and each foot cost $15, what will be the minimum cost? Okay, so let's take a look. How do we do that? So we can start with the minimum and we go through all the verdicts until we reach all the verdicts. That way we can find, or you just cross out the highest number in each graph. So this graph 6 is going to be knocked down. This graph 5 is going to be knocked down. This graph 9 is going to be knocked down. And let's see, after this one is knocked down, what is left over? If the graph left over is still something bigger, we're going to knock that out. Okay, so even I start on the top one here. Let's do the top one here. So I'm going to knock out this is biggest, so we don't go with the biggest. Okay, we're looking for minimum. And now still I have to open this up. So this is 6, so that is gone out. And up here, this is 6 is also biggest. So I'm going to cross that 6 out. Okay. And I have only one more graph. Clearly, as you see, so simple, right? And now I'm going to erase this one down here. Bingo. I'm done. Okay. I'm done. Clearly. So what is the answer? So my minimum spanning tree is going to be 4 plus 5 plus 4 plus 2 plus 4. That would give me 12, 17, 19. Now, if we read the question down there, right, it says 19 and each edge costs $15. So what do? we just multiply this 19 feet times 15. So in this case, we say 19 times 15, we're going to have total minimum cost $285. So that's how we find the minimum spanning tree. Thank you.